All right. So. All right. Okay. So I'm seeing some messages. All right. You see that little testing there. I'm going to. Oh. I'm going to work on it. Yeah. Yes, because actually, we were supposed to print the thing and have you come by the school and sit the exam, but because of COVID and all of that, we decided not to do that. So I'm going to devise another way in which you can do the test online properly. All right, I'm going to set it up, but I have to construct it in such a way, and it's time consuming to construct tests online. All right. So just hold the assessment on pause. All right, for now.
I'm sorry, Mr. Stevens, are you referring to the diagnostic test?
Right. I'm referring to the diagnostic test. So the initial plan for us was to copy the actual thing and for you to literally come by the school face to face and sit it. But it might cause some problems because we would want one sitting, and to get everybody to come at the school face to face may be a problem. So what I'm going to do, because right now as it is, some persons are WhatsApping me their answers, some persons are uploading their response in Google Classroom. All right. However, I'm going to construct the exam on a platform where you can actually just click on a link and actually do the questions. But it's going to take some time. I will try my best to have that assessment up by next class. All right. So
okay,
it's right. So suspend it for now. But what happens? It will be easy for you to do it. So all you need to do is go on a platform and everything will be there. As a matter of fact, you get your results instantly. All right. In other words, the computer will mark the thing for you. All right. Yes, go ahead.
I already read mine out of the WhatsApp group and did it.
I know, man. I know. So, some person would have done that already.
So, question, sir.
Yes.
Will it be a different form of test? Because I had already copied my set of papers from work, and the only thing I didn't do was the angles part, because brain was so fresh to remember the angles part.
What was brother?
Okay. All right. Ask question again, because I'm not sure if I'm.
If it will be the same test.
Yes. No, but it's going to be the same test. It's just that the test will be in the form. It will be computerized. You just go on it.
Star format. Okay.
Right. And you can go on it, and you'll get, when you complete the assessment, you'll get your grade instantly. But to construct it takes some time, especially with those diagrams. I actually started it, but I realized that I can't. I have to type out the thing myself, so it's time consuming.
All right, boss.
All right, but don't worry, man, you're gonna get it. And the reason, listen carefully, the reason we're doing this assessment is that I want to know where you are as a student, right? And also, I'm trying to lobby for an extra hour so we can have a tutorial session. So we can, you can come with your questions, we can practice past papers, anything. So I'm working on that also. All right. All right. Do we have any more questions? All right. Okay. Sir, I need assistance with uploading the work. All right. So.
You answer my question.
Okay. You're Ocean. Okay. All right.
Yeah.
Cool. All right. So are you guys seeing my screen?
Yes, sir.
All right, so let's ignore
Yes,
ignore that thing up at the top there. Some algebra. All right, so the objectives. I have a lot to cover today here because I didn't realize that we didn't do number theory. So we're gonna look at types of numbers. All right, types of numbers, and fractions, ratio, and hopefully SPA discussion. Hopefully, I don't know if I can do so many things in one, but let us see where it goes. All right. All right. So I hope you guys have your books out and your notebook. There's a 13, right?
Yes, sir.
All right, so this is our unit topic. All right, so take that down for me. All right, so types of numbers. So we have what we call natural numbers. All right, natural numbers. No, natural numbers, we use symbol n. We use, all right, let me just so natural numbers, you know, like 1, 2, 3, 4. So those are natural numbers. I should probably say set of natural numbers, because when you want to write sets of numbers, that's how you write sets in parentheses, in brackets. All right, and we use capital N to represent natural numbers. All right, everybody hear me clearly, and everybody seeing clearly? Are you guys hear me clearly?
Yes, sir.
All right, because I don't know, I bought a headset the other day, very expensive, and I realized that it doesn't work with Zoom. Can you imagine? I don't know.
Better to buy one cheap one.
Yes, but I want cheap one I use right now. But for some strange reason, it works on Zoom, it works on WebEx, Teams, everything. But when it comes, no, sorry, not Zoom. It works on Google Meets, WebEx, and Teams. But when it comes to Zoom, for some strange reason, it's just not working. All right. All right. So we have a set of whole numbers. All right. And we're going to use W. And with whole numbers, we start with 0. See the difference? So let me just put everything down here, so because so we have set of integers. All right. No, we don't use I. We don't use I. We actually use Z to represent integers. All right. But before I even talk about that, integers is really, so it's a set of either negative or positive numbers. Note, zero is neither negative nor positive. All right. So we use Z to represent integers. So, you know, -3, -2, 1. No, funny enough, even though we said that integers are negative and positive numbers, right? 0 is actually an integer. All right. I don't know why, but it is what it is. But 0 is actually an integer by definition. So we have natural numbers, we have whole numbers, we have integers, right? And we have set of rational. If I'm going too fast, let me know here. Am I going too fast?
No, sir.
All right. So we have rational numbers. Now, what are rational numbers? Now, any number that can be written as a fraction is called a rational number. So basically, you know, any number that can be written as a fraction, right? I know a fraction it's like this, it's like n over d. All right. All right, I want to know that d cannot be equal to 0. All right. So we know that n represents what? Numerator. And d represents the or when it says d is not equal to 0, it means that d cannot be 0. In other words, you can't divide by 0. Right? So any number that can bring as a fraction is called a rational number. We use symbol Q. So like negative, say 2/3. All right. So -2/3, that will be a rational number. Say a half. That's a rational number. It's 8/9. Let me ask a question. Is 0 a rational number? What do you think?
No.
Look at the definition of what a rational number is.
I say no.
All right. Anybody else? Not sure?
Yeah, I would say no.
I would say no, sir.
Mhm.
No, sir.
I think, okay, so I think what you should ask yourself, you see, what you should ask yourself, can 0 be written as a fraction?
Exactly. And no.
I'm going to disappoint all of you, you know. You can actually write.
Can
Yeah, man. Oh, you write 0 as a fraction.
I?
You write 0 as a fraction as 0/1.
That makes no sense.
Really?
Yeah. Can 2 be written as a fraction?
Yeah.
Yes, sir.
Or you write it? It will be what? Or you write 2 as a
2
fraction?
over 1, sir.
2/1.
Cool.
The 0 is first. May I say that?
Class me
At first, me I see that too.
Yeah.
I think someone needs to mute their mic. Please.
Davin.
All right. What about -5? Can you write -5 as a rational number? Is -5 a rational number?
-5.
Yes, sir.
Can I write as a fraction, sir?
Yeah. How you write? Oh,
Sir. -5/1.
right. It will be -5/1. All right. All right. Any questions? All right.
I guess as we go down into it, sir, you're gonna explain how the 0 come in, because right?
You mean why, like why 0 is a rational number?
Yeah.
Well, because you can write 0 as a fraction. You think about it, the definition. What's the definition?
Yes, sir. All right. A fraction is like having, right? Let's first say, for example, you have a pie, and the pie is cut into 4 pieces. I give away 2 pieces, so you have 2/4. How is it 0/1 coming in? That I mean, I understand. You're gonna say you have 1 pie and you didn't share it, so
Exactly. The same result. You didn't share the pie. And that's why 0 divided by 1 is equal to 0. You get what the same 0.
okay.
All right. So you explain yourself. All right. So for example, 2. All right. I mean, how do you have 1 pie? How, you know, it says 2 divided by 1, and that will give you back what? 2. All right. All right. Any questions? I think the thing about it is once you can write it as a fraction, it is called a what is it called? Irrational
Rational
Rational numbers.
Right. So, you know. All right. No, let's look at something here. No. Somebody want to say something? Remember to mute your mic, please. All right. All right. Now, let me ask a question. Listen carefully. Are all natural numbers whole numbers? Yes or no?
Yes.
Numbers are whole numbers.
Yes, sir.
No, sir.
No,
No,
sir.
sir. No.
All right. Let me say it again. Oh boy, I'm getting negative feedback. Oh dear. It's like someone is swimming. Anybody is swimming in math class, like, you know, you're in a river or something. All right. Okay, let me ask a question again. Are all natural numbers whole numbers? True or false?
Yes, sir.
Yes, sir.
True.
Yes, true.
Yes, sir.
True.
Yeah, but yes, it's true because all natural numbers are contained in what? The whole numbers. All right. So as you can see, natural numbers are what? 1, 2, 3, and 4, and 5, and whole numbers are 0, 1, 2, and 3. So the 1, 2, and 3, 4 in the whole numbers are the what? The natural numbers. All right. So we can safely say that natural numbers are contained in whole numbers. As a matter of fact, we could say that natural numbers is a subset of whole numbers. All right. Okay, let me ask that.
Before you move on, sir, can I ask a question? Just in case this run by me again. The zero part is what I'm not getting with this. No, man, same place I said natural numbers and whole numbers. You said they're basically the same thing, right?
No, I didn't say that.
Okay,
Idiot. Zero being a natural number.
Brittany, I hope you didn't know. I hope you didn't say that to our student.
Okay, so the zero, no. You said zero is not a natural number?
Yes, according to the definition.
Okay.
All right. So no, zero is not a natural number because there's no zero in the set, according to the definition. All right. All right. Now let me ask another question. Would you say that integers are whole numbers? Or do we have whole numbers in integers?
Yes,
Yes,
sir.
yes, sir.
Yes, look at it. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4.
Because it both contain negative and positive numbers.
Right, cool, right. So what you notice? Natural numbers are contained in what? Whole numbers. Whole numbers are contained in what? Integers. So let me ask you a question. All right. Do we have natural numbers in integers?
Yes, sir.
Yes, because if it is contained in whole numbers, it must contain in what? In integers also. All right. Is everybody following?
Yes, sir.
Right.
Yes, sir.
So natural numbers is a subset of whole numbers, and whole numbers is a subset of what? Integers. All right. All right. Let me ask a question. Would you say natural numbers, whole numbers, and integers are rational numbers?
Yes,
Yes,
sir.
Yes,
sir.
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 Yes, because if it
Yes,
is
sir. And they can make it
exactly, because they can get, because remember, rational numbers, they're negative numbers, and all right, hold on it. I'm getting a negative feedback. Oh dear. It's like this person background is so noisy, like, oh my. All right, so if you're not gonna talk, please mute your mic, please, sir. All right, thank you. All right, so as I was saying, you see, natural numbers, whole numbers, integers are all what? Rational numbers. All right, because look, 0 is a whole number, but can you write 0 as a fraction? Yes, and if you can write 0 as a fraction, then it's called a what? A rational number. Get it? And look at -3. -3 is an integer. Can I write -3 as a fraction? Yes, it is going to be -3 over 1, which is a rational number. All right. All right. Is everyone following? Any questions? Any concerns?
Even Mr.
Yes.
Stephen.
Yes, boss.
Yeah, just being able to log on. I just wanted to run down what the topic that we're covering.
All right. So these are the things that we hope to accomplish by the end of the class. We're looking at types of numbers right now.
Types of numbers. Okay.
Right, types of numbers. All right, so, and this is what we have done so far. All right. All right, then now we have what we call a set of irrational numbers. All right. And many probably might don't remember. You'd have probably learned all of this in primary school. I know you don't remember, but you'd have learned all of this in primary school. Now, what are irrational numbers?
Would it be like negative?
Negative, positive. Well, negative and positive is reserved for, well, I mean, negative and positive what?
Sir, I think it's numbers that cannot be written as a fraction.
Sir, is
Thank
it numbers
you.
that
Right. They're numbers that can be written as a fraction. That's awesome. All right. So irrational numbers are numbers that cannot be written as a fraction. In other words, hold on, guys. In other words, oh boy, my machine is using up a little bit. All right, and let me just remind you, ladies and gentlemen, to be courteous to our classmates and you know, just let us be polite, let us be respectful, let us, you know, let us not let us be respectful, all right, and not say things that are, even if someone don't understand, don't ridicule anyone, all right. All right, so my machine is a bit frozen right now. I'm just waiting for it to unfroze. All right, so I think it's good now. So in other words, give me a second. In other words, when they can be written as a decimal and not recur, or they are recurring decimals. Anybody know what a recurring decimal are? What they are? All right, let me show you. All right, so let's say I have 1 divided by, say, 3. All right. So suppose I want to work this out. I'm going to do long division. So 3. All right. No, you're going to say 3 into 1. You know, we can't. So we put a point there and we'll put a 0 there. All right. And we say 3 into 10 goes what? 3 times. And we said 3 is what? 9? No, it's not 6. 3 3s is 9. And then 9 from 10 will give us what? 1. But then no, we said 3 can't go into 10, into 1, sorry. Then we put a 0 there. And we said 3 into 10 goes what? 3. 3 3s, 9. Subtract the 1. Well, you notice? It's going to keep going and going. Right. So we call this a recurring decimal. So for example, so once you have a recurring decimal class, it's called a irrational number. So 1 over 3 is called a what? Irrational number. Because it's the decimal, if you were to write this as a decimal, it keeps on what? Going on and on and on. It's a recurring decimal. Now, suppose it wasn't a third. Richard, can you mute your mic for me, please?
Okay.
Chief, Tamia, can you mute your mic for me, please? Right, I'm seeing all those mics are open. You know, I'm available. I can see them, right? All right. All right. So, oh, what did I lose that? At least, oh my, I lost that. You know. All right. So, for example, 1 over 5, 1 over 2 class. 1 over 2 is what? 0.5, not true? No, does it is it 0.555? Or
No,
is it 0.
it will be just 0.5.
Okay, so it stops right there. So it's a non-recurring decimal. So we would say a half is a what? A rational number. But 1/3 is a what? Irrational number. Because it keeps on going and going and going. All right. So every decimal that is a recurring decimal would be a irrational number. All right. Is everybody following?
Yes, sir.
Yeah, man.
Yes,
So,
sir.
and remember, on every fraction. All right, let me show you something. We said that rational numbers can be written as a fraction. All right, but look at 1/3. 1/3 is a fraction, not true? But it wouldn't be a rational number because 1/3 is a recurring decimal fraction. So I'm saying. So probably this definition probably needs to have a disclaimer, you know. All right, so we will venture off into irrational numbers. So what I'm going to do, I'm just going to give some examples. of irrational numbers. And the symbol that they use for irrational numbers, no, it's not I. It's actually, oh, it's I, you know. Let's see. So I is equal to say 1/3 negative. Anybody know what a surd is? Surd, S-U-R-D.
Don't recall hearing that term.
No, sir.
Don't recall? All right. Anybody know what a square root sign is?
Yeah, I'm familiar with that.
Right.
Yes, sir.
Right. So the name, wait, let me show you something. It's a square root. You have different types of roots, you know. You have square root, you have cube root, you have fourth root, you have, it goes on. So all those are roots. Now all of them are called what? Surds. But some persons just think that is a square root alone you have. All right, so you have cube and fourth and fifth and all them something. All right, so that symbol is called all those symbols they're called surds. Let me just put it in bracket. Surds. Anybody know? Let me see if we can find it. Anybody know what that symbol is called?
Pi.
Pi, right?
Sir.
Right. No, pi is also a irrational number. If you go on Google or even YouTube and type in pi, you'll discover that pi never ends. The number keeps on going on and on and on and on and on and on. All right, it's a mysterious number. So pi is also an irrational number. All right. So these numbers are not, they're not random. You have to study them and realize that, boy, the decimal will recur, not true? Yeah. They're not random numbers. All right, so these are some examples of some irrational numbers, sorry. All right. So we have another type of number, set of real numbers. Set of real numbers. No. What are real numbers? So if you have real numbers, then what are all these numbers called? Unreal? So a set of real numbers is a combination of rational and irrational numbers. So when you combine rational and irrational numbers, class, what do we get? Real numbers. All right. And we use the symbol R. So R represents real numbers. As you can see, it's everything, not true? It's everything. So real numbers. So remember, watch out now. Let me show you something. Remember, rational numbers covers all them numbers, not true? Rational covers all those numbers, and irrational numbers covers the rest. So if you're to combine rational numbers In other words, if we're to combine all these numbers and the rest, what you get, class? Real numbers. All right. Nobody following? Any questions? All right, so what I'm going to do, I'm going to draw a diagram to represent the it's like a summary of everything. All right. All right, so this is kind of difficult to do on a computer, so I'm just going to draw it. All right, so we have a little box. Oh boy. All right. Now our first circle is natural numbers. All right, and then our next circle, and we notice the first circle is contained within the other circle, which is whole numbers. And then we have another circle. So natural numbers is in whole numbers, and whole numbers is contained in what class?
Natural number.
Integers. All right. And then now everything is contained in rational numbers. Rational numbers. All right. Now, so you have natural numbers containing whole numbers containing integers, and integers containing what? Rational numbers. So natural numbers, whole numbers, and integers are all rational numbers. Now, every other number outside N, W, and Z and Q would be irrational. All right. Now, obviously, I can't put another circle right there. So, why I can't put another circle right there, so, and call it irrational? Why would this be wrong?
Because what is inside of the circle is rational numbers. Let's put it outside for the irrational numbers.
But no, I'm asking you why.
Because irrational numbers covers all of them, so it would remain the same as rational and irrational.
I'm not
Because
sure. Hold on. Let me rephrase the question. Hold on, my boss. All right, so listen carefully. Natural numbers are whole numbers. Whole numbers are integers. Integers. Hold on, I missed out something. Natural numbers, whole numbers, integers, and Q is what? Rational numbers, are true? Now, what I'm asking you, why is it that I cannot put a circle, another circle, and call the circle irrational numbers? Why would this be wrong? Why I can't do that? That's a question. In other words, if I want to represent irrational numbers, I can't draw a circle like that.
Because irrational numbers cannot be written as a fraction. That's why you wouldn't do it.
Not, well, what you're saying is true, you know, but it doesn't answer the question I'm asking you right now. You get it?
Because rational numbers are positive.
Mm-hmm.
And irrational numbers are negative.
No. All right. Let me just. Somebody needs to mute the mic.
It can be written as a decimal, sir.
Because?
It can be written as a decimal.
No. All right. Anybody else?
Yeah, I want to give it a go. So you can't pair it with irrational numbers because they either continue or has to be written as surds.
What is it when it has to be continued? What does that mean?
As in, it doesn't stop at when you actually divide or break down half, you actually get 0.5. With rational numbers, they continue as in their numbers goes on.
Okay, all right. So what you're saying is correct, but what I'm asking you, the answer is incorrect. It's like you're answering something that is true, but not relevant to what I'm asking. All right, let me just say this.
Sir.
Yes.
Is it because all the numbers is a combination of rational and irrational numbers?
Say it again. Because
the sets are they are real numbers and they're all a combination of rational and irrational numbers.
Okay, what you're saying is true. All right, guys. Let me say the question again. The question is, look, I have. Would you agree that this circle represents everything that is true? Does this diagram represent what is true about natural numbers, whole numbers?
Yes, sir.
Yeah. So what I'm saying is, if I draw another circle and call it irrational, why I cannot draw that circle there? But you guys are telling me what the definition of what irrational number is. But I'm asking you why, if I draw a circle here, so it will be wrong.
Sir, is it because what you're drawing
Because
right there is going to...
Hold on. Somebody's speaking, Mike. All right, somebody's on the floor here. So just allow the person who's speaking to speak. All right. Is that clear?
Yes.
All right, let Miss Clara go.
So I don't know if I'm right, but I'm saying, is it because...
Hold on. Too many mics are open. Tamar, Novia, come on, guys. I'm hearing a lot of. Just mute your mic if you're not speaking. All right, go ahead for me, Clark.
So if the I is out there, it's going to say that the N, W, Z, and Q is related to the I. So the I cannot be out there because it's not. They're not considered as irrational numbers. I don't know.
You're correct. Basically, yes, that's true.
Okay.
If I put the I right here, sir, right, which is irrational, what is it, It's saying natural numbers, all these numbers are also what? Irrational, which is incorrect.
Irrational, yeah.
Which is incorrect. So I'm saying, class, so you can't put the circle here, because if I put the circle here and say irrational, it would mean that natural numbers are irrational numbers, whole numbers are irrational numbers, and real numbers are irrational numbers, etc., etc. You follow? So I can't put the circle right there. So it would mean that N, W, Z, and Q are contained in I, which is not true. Everybody follow?
No, sir. Could you repeat?
Sir.
Yes.
All right. Somebody said I should repeat the reasoning, the answer?
Yes, sir.
Yes, sir.
All right. Okay. Yeah. Somebody saying something?
Yeah. So what you're saying is that, all right, due to the fact that I is out there that irrational numbers. So you're saying that, for instance, like Q is rational numbers. So everything underneath Q, like natural and so forth, is basically under rational numbers. So because outside and because if I put I outside, that means everything else below that would be irrational. Which
exactly.
That wouldn't be the fact. Would be.
You said it correct.
Okay. So because everything else is already rational, you can't put I outside to actually change up everything.
Because if I put I outside, you know what I will be saying? I will be saying rational numbers are irrational numbers. Not true, which is not so. All right. Yeah, you got it correct. Yeah, the person who said that I should explain. Do you still want me to explain?
Yes, please.
Oh, okay. Person still want me to explain. All right. Okay. Now, do we agree that natural numbers are contained in whole numbers? True or false?
True.
Yes, sir.
All right.
Yes, sir.
Do we all agree that whole numbers are contained in integers?
Yes,
Yes,
sir.
sir.
Right. Now, do we agree that integers are rational numbers?
Yes, sir.
Yes.
Agreed.
All right. No. True or false? Are rational numbers contained in irrational numbers?
No.
No. No. What is an irrational number? An irrational number is a number that cannot be written as a fraction.
The
That's how I
opposite
go.
of rational.
It's the opposite of rational. So I can't have I right there. So do you follow? All right.
Yes.
Yeah. All right. So but where do we put it though? Where do we put it?
Outside the box.
Outside the box.
Well, no, you wouldn't put it outside the box. What you probably do is just that you could shade outside yourself. So everywhere outside yourself within the box. So all of that would be what? I. Because remember saying, so Q cover everybody right there, so protect everybody right there. So everybody outside the circle would be what? I. It's like the black sheep in the family.
So Q is contained in I.
Sir, I think it's confusing if you leave I out there because of this. So you did have I, when did I ask the question? So if you draw a circle for I itself, probably would be much clearer.
Yeah, because now we are thinking that Q is contained in I.
Yeah.
No,
if you circle draw it at that time,
no,
you
man.
think it could go.
Remember saying circle different from rectangle, not true? All right, suppose this circle represents a pool of water, right? It's a pond, right? This is a pond of water. And right here is a different shape. Would you agree it's a different shape?
Yeah.
It's a different shape. So the different shape would represent something that is different. So this I would be like the grass. All right, I understand what you're saying. You're saying that it's kind of containing, but it's not because the shapes determine the difference. You follow?
Yes, sir.
Yes, sir.
All right. If I were to change this, I'll be changing mathematics. All right. So I can't really draw a circle here. If I draw another circle, it would
Okay.
All right. So
I have a question. Good evening.
Yes, good evening.
So, what would you use to differentiate? Because if Q is not a part of the circle and it's not a part of the other shaded area, then
no, man. Q is a part of the circle.
Okay.
Yeah, man. This is Q. The biggest line, the biggest circle is Q.
Yeah, but it's still agreeing with my fellow classmate. It still kind of seems as if it is in the same space as I.
All right, but the thing about it, I use circles to represent N, double Z, and Q. But for I, it would be a different shape. It's a different. It's a space outside.
O, the person's name O. You can think of it as you see the small circle in the middle there, so that's N. You see the next circle, that's W. You see the next circle, that's Z, and the next circle and the Q. Just think of it that way. It's not in a circle, it's just labeling the circle.
Okay.
All right. Okay. I hope boy, you guys are really delving in this thing. I've never actually delved in this in so much, but it's pretty
Maybe
interesting.
because you have so much female, we think hard or shit.
All right. Okay. All right. But as I was saying, guys, the reason why we have I on the outside because it's represented by a different shape. All right. Let me. All right. I was going to show you a practical question that you probably would able to relate this to. All right. Okay. Now, so we said that I is on the outside. So I is everything else other than what's inside these circles. Okay. Now, what's the definition of what a real number is, class? What's the definition of a real number? A real number is a combination
Combination of irrational and rational
of
numbers.
irrational and irrational. In other words, real numbers covers all of the circle. All right. And real numbers cover the grass too. And the grass represents what? I. All right.
So the real numbers is the triangle basically.
Exactly. So is it no, it's not a triangle. I almost say yes. Right. The rectangle. And what is contained in the rectangle, class? The circle and the what on the outside of a circle, not true?
Yeah.
Right. So you see the rectangle now? The rectangle itself is called R, which is the real numbers. All right. And in what you're going to learn further on is that the rectangle is what we call the universal set. So the universal set is a set of all the elements. All right. So real numbers will be the set of all the elements, every possible element you can think of. All right. Okay. Any questions? All right. Please jot this down. All right, guys, give me 3 minutes here. Assume about. All right. Let's continue. All right. So we're going to look at some meanings of 0. All right. So 0 is used to represent an empty or null space. 0 is the midpoint on a number line. So 0 is a midpoint on a number line. So I would have mentioned this already. So 0 is neither positive or negative. The additive identity is 0. What does that mean? 3 plus 0 gives you back 3. 8 plus 0 gives you back 8. In other words, any number added to 0 gives you back the original number. So that's what we call the additive identity. So the additive identity is 0. What to follow?
Yes.
Yeah, man. Any number added, any number added to 0 gives you back the original number. All right. So the term that they use to describe all of that is called your additive identity. Any number multiplied by 0 is what? Anybody knows? Is what?
0.
Is 0.
0.
Example 10. Example 10. 10 times 0. 0. What about 3 over 8? 3 over 8 times 0 will also give you what? 0. What was 0 point that? That is also 0. All right. What about a while ago, we said that we can write 0 as a fraction, not true? Correct?
Yes, sir.
Right. So 0 divided by say 15. What is 0 divided by 15? 0. Follow? What is 0 divided by say negative 26? That's 0. However, what's up? Suppose I put something like, oh boy, that's not the wrong place. Suppose I have, say, 21 divided by 0. What is that? Somehow would a calculator do that for me? What does the calculator say?
Cannot divide by 0, sir.
Error or syntax error or you might see E, or you might see undefined. All right. So in other words, we cannot divide by 0. It is undefined. Undefined means that it does not exist. What's up here? All right. You guys following?
Yes, sir.
Yes, sir.
All right. Okay, so we have something called, so that's 0, right? There's something called the multiplicative identity. All right, so we have something called the multiplicative identity. What does it mean? So this means that, well, when I use earlier on, when I used the word additive identity, what did I say? What happens? Additive identity means that you must get the same. You must get the same answer, same question, not true? So you start off with 3, and we end up with what? 3. So if I say multiplicative identity, we're talking about which number can we multiply by and get that original number. Ten multiplied by what number gives you back 10?
1.
1, right. So we say 1 is a multiplicative what? Identity. So 1 is the multiplicative identity because when we multiply by 1, get back the original number. example, the 6 times 1 gives you back what? 56. 0 point that gives you, hold on. Times 1 gives you back 0.8976. All right, etc., etc. 3/4 times 1 gives you back the same thing. So we say 1 is a multiplicative identity. All right, now you have something called the additive inverse. Additive inverse. All right, now the additive inverse, so this is just a number when added to the original number gives us 0. Everybody have this notes on multiplicative identity?
Writing it
No,
up.
sir.
All right, let me just bring it down. Let me just bring it downstairs. All right. All right, so additive inverse, you see, is just a number when added to the original number gives us 0. So example, let's say 7. Class, let me ask a question. 7 plus what? 7 plus what? 7 plus what number gives you 0? What would that number be?
7 plus negative 7.
All right, correct. Negative plus negative, sorry, 7 plus negative 7 gives you 0. All right, and what really happens here is that I might be saying something that some of you may not know of, but probably some of you may know about it. So what happens is that when you multiply a positive times a negative, you think about it, all right. Carry on, can you mute your mic for me, please?
Oh, I'm sorry.
Yes. Please, boy, a lot of mics are just constantly open. Today is a lot of open mic day. All right, so 7 plus negative 7, right? We say it gives us 0. Because when you multiply, you see brackets mean multiplying. If I say 2 bracket 3, it means 2 3s, which is what? 6. But if I see these two signs, I'm going to use what we call the rules of multiplication, which states that a positive multiplied by a negative gives us a negative. All right. So these two symbols become 1. So we end up with 7 subtract 7, which is equal to 0. Everybody follow? So if I ask you what is the additive inverse of 5?
Yeah, if you could just reiterate that.
Please.
All right. Okay. Let me just finish this point. If I were to ask you what is the additive inverse of 5, what would it be?
Negative 5.
Negative 5. So in other words, if the additive inverse of any number is just the original number, but just put a negative sign in front of it. That's all. All right, some persons are saying that I should explain again. All right, so basically, you want me to explain this part here again? That's what the problem is?
For me, it's the way you illustrated it at the part thereafter with the 7, the plus, then the multiplication sign.
You mean down here, so? That's what you're talking?
Right.
All right, so yes, yeah, it's not the way I illustrated it. It's what's fundamentally mathematics. So yeah, I'm just giving you a rule that already exists. So these are rules, right? All right, what is a negative times negative?
Positive.
Positive.
Right. How do you know that? It was a Aris, can you mute your mic for me, please? Please, guys, you guys are giving my ears are hurting. Adrian, please mute your mic. Oh.
Sorry about that.
All right. So negative times negative, we know is what? It's positive, not true? Where did this come from? It came from a set of what? A set of rules. All right. Rules. So, and these rules, you know, I don't know if you guys remember this, but this should have been taught to you in high school, like grade 8, grade 7, or grade 8. All right. So this is just one rule of 4. Negative times negative gives you a positive. So when you multiply 2 negative numbers, you end up with a positive number. What about positive number? What happens when you multiply a positive number times a positive number? What do you get? Like 2 3s, 2 times 3. What sign? Another positive, right?
Positive, sir.
Right. So this was another rule. That's another rule, not true? All right. And I am simply explaining to you that this, what I'm having right here, so is just another rule out of these rules of integers. Now, this rule says that a positive number times a negative number gives you another negative number. That's this rule. You may not remember it, but if you remember these two, there are 2 others. So a positive number times a negative number, class, gives you also a negative number. And the other rule is negative number times a positive number gives us another negative number. So these 2 rules are pretty close. It's just if you flip around the signs, you still end up with a negative. All right. Did I lost anybody?
I think I'm following so far.
All right. Anybody lost? Any clarification?
No, sir.
All right. All right.
But just a quick question on the rules there. I wouldn't mind, probably after class doing a quick review of some of that so that I could just get a grasp, specifically on the rules, because I think that would be like a crucial guide to this topic. I'm more than if any videos you might have shared might, contain those.
All right. Well, actually, we're not really looking at these rules right now, but it just happens that in order for me to explain this concept here, I have to use those rules. I do have a little video clipping on this, but we're not actually doing, this is not really what we're teaching right now per se. All right.
Okay.
You understand? So when we start to do integers, then we will get into it. All right. But these are the 4 basic rules when you multiply integers. All right. Because most of you know negative times negative is what? Positive. And positive times positive is also positive. But you have 2 other rules. Positive times negative give you a negative. Negative times positive gives you a negative. All right. And really and truly, I'm actually using this particular rule to explain why these two signs become one, which is a negative. That's the whole point. So these two signs, when you put them together, when you multiply them together, class, what you get one sign, which is a negative. And 7 from 7 will give us 0. All right, so therefore we say that 7 is the additive identity for 7. And the additive identity for 5 is what, class? Negative 5.
Otherwise known as the integer.
Well, yeah. Well, all of them are integers. Remember, integers are negative numbers and positive numbers, right? So 5 is an integer, and negative 5 is also an integer. All right. So integers are not negative numbers, you know. Some people have that thought. Integers does not. It is not only negative numbers. It's positive numbers also, right? All right. Any more questions? All right. So we're looking at the additive inverse. Additive inverse. So the additive inverse of 7 is negative 7, because when you add those two, what you get? You get 0. What is the additive inverse of 13.8, class? What is it? What's the additive inverse of 13.8? What do you think?
Negative 13.8.
Negative 13.8. Because when you do that, you get 0. Because remember, when you put these plus and minus together, you get one sign, which is what? A subtraction sign. And 13.8 subtract 13.8 will always give you what? 0. All right. Are we understanding?
Copy that.
All right. What about let me see if you guys are really. Let me see. Suppose I say negative 6. What is the additive inverse of negative 6? What can I add to negative 6 to give us 0?
Positive 6.
Positive 6. Anybody want to explain how we get 0? Why negative 6 plus 6 gives me 0? Why is that so?
Is it because there's a negative, then you have a positive?
Go again for me, please. Go again.
Is it because there's a negative before the number itself? So you have a negative 6.
So isn't it supposed to be negative 0?
Hold on. boss. Somebody's talking, you know, so allow her to finish her thing. All right, and then you can ask, you can make a comment here. All right, sir. Is that fair enough?
Yeah.
Right. When somebody is speaking, please don't do that. Here, I'm begging you, because she's on the floor, she's making a point, so don't interject until she's finished. But to answer your question though, 0 is neither negative nor positive. All right. Go again, miss.
Okay, what I was saying, seeing that there's a negative in front of the 6, it could be a whole number in my mind. So you'd have a negative plus a negative 6, which is no what is that? Integer?
Well, I mean, negative 6 is an integer. Positive 6 is also an integer. They're all integers.
Okay then. All right, so you have a negative plus. Once you have a negative and a plus, you will get a negative. If that makes sense.
All right. Unfortunately, it's not making much, because you're saying once you have a negative and a, come again. Once you have a negative. All right. I think about it. You're not giving me a reason. It's like you're just restating like whenever there's a. All right. Basically, I understand what you're saying now. Because if I say, hold on. If I say negative, say 9, right? If I say negative 9, and I ask you, what can I add to negative 9 to get 0? You're gonna say plus what? 9. So I'm asking you, why is that so? But you're saying that, boy, once you have that situation, then you get 0. I think that's what you're saying. You're saying, boy, once you see that, then it must be 0. But it's not answering the question why. So I'm saying, so what you're saying is true, you know. Once you see that, you're gonna get that. But if I ask you why, it doesn't answer the question why. But when you see it, you just know, so boy, that is supposed to get. All right. Am I making sense?
Sir, can I give it a try?
Hold on. I think somebody else was saying something. The person can go ahead. I think a young lady was saying something, and I stopped her. You can go, miss. I don't know who. Was it you? Were you the person?
No, it was the male that was trying to say something.
It was a male.
Yeah, it was a male.
All right.
Yeah, I was just saying that negative, as you're saying, no, -6 plus positive 6 equals 0, right? I'm saying that the 0 would fall on the back and the whole number, so it wouldn't contain any negative or positive.
Okay, true, correct. But you're not answering the question. Why -6 plus 6 gives you 0? You're just saying, you're just telling me a property of 0.
Because it's the rule.
It's the rule. All right. Okay.
Sir, is it because -6 is basically 0, because when you have a negative number, it doesn't, it's nothing, it's not. But when you add a positive to it, then it cancels out the negative and becomes
not again.
So say for example, you have a negative 6 in your bank account,
right?
Which is overdrawn, and then you add $6 with which cancel out the negative.
You're getting somewhere, yes.
Give it back 0 back.
You are
give
correct.
Give it back $0 in your account.
Yes, I think you initially you said something, but I guess the words didn't come up. But you actually explained it beautifully with that scenario about the bank account. All right. So for example, negative means you owe. Am I correct?
Yes, sir.
Right. So I'm gonna try to explain this. Negative means you owe. All right. Now, suppose you say. Suppose you have a little corner shop. You guys have a little corner shop in your neighborhood? And this is Brown's Corner. This is Brown's Corner Shop. I don't know why I'm using that name. I hope I don't offend anybody.
Good business, man.
Oh, yeah, sir. It's one thing though I don't like. It's one thing I don't like. When it's something you call them, like them just bakes up on what you want. So.
Sorry, we're in there. Shop hot, sir.
Shop what? All right, hold on. Shop what? Hey, I put in an AC in the shop, man. Watch it. AC. BTU unit. And if you want, you can put a little dish up there, so. Right. All right. So this is Mr. Brown's shop. All right. Now, let us say you went to Mr. Brown and for some reason you owe Mr. Brown some money. You owe Mr. Brown $6, right? Mommy now, or daddy, mommy now gives you $6. So so $6 big. Now mommy gives you $6, right? But you owe Mr. Brown how much money? $6. So you take the $6 to Mr. Brown's shop and you pay. Pay means you add. You add on, not true? You add on the same $6. How much do you owe Mr. Brown? You owe him?
$0.
Nothing. Everybody
You're
follow?
debt free now, sir.
Huh?
You're debt free.
The success I'm debt free. Debt free. Yeah. You're debt free. Yeah, you're debt free. Yeah, you're debt free. Yeah. All right. Now, let me ask a question. Suppose that mommy get money, and mommy give you $10 to carry a Mr. Brown shop. Remember now, you know, you still owe Mr. Brown $6, and true. All right, so you owe Mr. Brown $6, and mama give, how much money mama give you? $10. So you're gonna go to the shop now and give, as in plus, you're gonna give Mr. Brown $10. What Mr. Brown gonna do now, class? What do Mr. Brown gonna do?
Give them back your change, sir.
Give back your $4.
Right. Mr. Brown. Right. Mr. Brown is going to take his $6 that you owe and give you back change. So it means that you're going to have $4 change. You follow?
Right.
All right. Yeah. You get it?
No.
Fully.
All right. What part you don't get? The whole thing?
Yes, sir.
All right. Do you understand? Do you understand the part? All right. Do you understand the story that I'm trying to create here?
Yes, sir.
All right. Do you understand when I say you owe Mr. Brown $6?
Yes, sir.
Do you understand when I say that mommy gives you $10?
Yes, sir.
Yes, sir.
All right.
Yes.
Do you understand when I say you go to the shop and give? Give means what? Plus. So you're gonna give $10. Do you understand the statement here?
Yes, sir.
All right. No, imagine now you're at the shop, right? Have you been to a shop? Do you go to a shop? Have you? No? Or you just call delivery service and swipe out your card, and so you're at the shop with the $10, right? Mr. Brown, no, Mr. Brown is gonna take his what? He's gonna take out his $6 out of the $10, sure. Would you agree?
Sir.
Yeah.
Yeah.
What happens when Mr. Brown take his $6 out of the little girl's $10? What's gonna happen?
I'll give him back his change.
Give back him change. And what is our change?
$4.
$4. Are you following it now?
Yes, sir.
You know, some fee say understand the whole thing, because 99% is something you say understand. All right. But let me give you another case. Right? Suppose you owe Mr. Brown $10, right? You still owe Mr. Brown $10. And let's take mommy out of this stuff. All right, you owe Mr. Brown $6, right? And Mr. Brown know you from long time. And Mr. Brown know your mother and everybody, and most of you're not thief and you're good people and you're church people and all of that. You know? Let us say you owe Mr. Brown $6, right? The little girl is coming from school. Is very thirsty. All right? And she wants bag juice. All right, and let us say the bag juice costs $10. All right, so she's gonna go to the counter and say, Mr. Brown, I need a bag juice. And Mr. Brown said, where money there? The girl said, no money. Spend up on sweet and something. So, can I get a bag juice? I'm really thirsty. Mr. Brown, all right, no problem. Just like a bag juice. All right. So what happened is that Mr. Brown, when Mr. Brown gives the little girl the bag juice, would you agree with me that this equation would represent the scenario of Mr. Brown? Would you agree with me?
Yes, sir.
Yes. Because the little girl owes Mr. Brown $6 already, you know. Correct? And then yes, guess what? She go to the shop now, and because of circumstances, she just need a bag juice. But she don't have the money. But Mr. Brown gave it to her. All right. So she owes Mr. Brown what? A $10. Now, if I were, so she owes Mr. Brown how many times? 2 times. Now, if I were to ask you to work out this equation, what would the answer be?
Negative 16, sir.
You want to explain why? Explain why.
Because then you would add the negative 6. Then you would add the negative 6 to the negative 10.
Cool. In other words, you
owe
negative 6. Right. You
Sir,
owe,
in working that out, right? In writing it rather, because I came up with the same answer, but I was thinking that you were going to add a plus sign before writing the negative 10.
You can, you know, but I didn't want to complicate it. You know why? Because I then would have to go into something more, some more stuff.
Okay.
I didn't want to go that route.
Okay.
But then no, you know, I'm trying to explain it based on her, because then you're gonna say you're gonna add negative 10. It can work, you know, but not necessarily for this case. And you guys are absolutely correct. You owe $6, you owe $10, you owe a total of what? $16. Everybody following?
And it's still negative because I don't get my money yet.
Exactly. How can you make Mr. Brown debt free? What little girl can do?
Give me $16 come.
Right, add 16 to it. And if you add 16, what are you gonna get? 0. You're debt free. All right. So class, let me ask a question. If I said to work out this, what would the answer for this be?
7.
It will be
7, sir.
Somebody explain to me why they get 7. Using Mr. Brown scenario.
Because I owe Mr. Brown $3 and I somehow have $10 and I want something from the shop. So I give Mr. Brown my $10. Mr. Brown takes the amount that I owe him and give me back my change.
Thank you very much. Everybody following?
Yes, sir.
Suppose I said to work out this. What would that be?
Negative 9.
Negative 9.
Negative 9. Somebody explain to me using Mr. Brown's scenario.
Well, Mr. Brown, $10. And I send $1 to give him. So you still owe $9.
$9. Exactly. And if you have something like this, negative 7, negative 3, negative 10. What would this be, class? Somebody tell me.
Negative 20.
Negative 20. Mr. Brown come with a machete, you see? You owe Mr. Brown. How much time you owe Mr. Brown? Three times. You understand? Hey, next thing you know, you can't pass in shopping, you have to find a shortcut.
That's like 3 different scenarios right there.
It's 3 different cases. Yeah. All right. Okay, so I would have diverted a little bit. All right, so we're talking about additive what? Inverse. So additive inverse is a number when added to the original number gives you 0. All right, so the additive inverse of 7 is what, class? Negative 7.
Sir, may I make you ask a question, sir? is the case that you have to put the bracket or no?
All right, so you don't have to put the bracket, but I put it there because I want to separate the plus from the minus, so it's easy on me.
So question, sir.
Hold on. Are you following? Hold on. Are you following, sir? So the reason I put the bracket there is because I don't want it mixed up with the plus. That's the reason.
When you think bracket basically was there for, even though you're trying to separate them, it was kind of identify maybe a multiplication or something.
It does, because yes, but that's what I was saying, because it's whether you have a bracket there or not a bracket, it means the same thing. Because if I were to write this without the bracket, you'll have 7 plus minus 7, which is the same thing as 7 plus times negative 7. So you still have to multiply these two signs. So the bracket just reinforces the concept of multiplication. All right. But in many cases, then they're gonna put the bracket there. All right, I believe somebody was saying something.
The format you're using right there, so nowadays 7 plus bracket negative 7. You still say that fall on a bad mass same procedure?
No, because we're multiple. No. Bad mass is all right. Is it this? The plus. Let me tell you what bad mass is. Bad mass is something like this. Like you have 7 plus 5 subtract 9. That's what bad mass is. When you have different signs between the numbers, like 7 plus. So in this case, you use bad mass, but what we're dealing right here, so is say 9 plus minus 7. So you notice the two symbols are together, not true?
Yeah.
But the symbols are separated here. So you use bad mass there. So. But when you have a situation like this, all right, it's something different. Okay. Basically, let me tell you something. You can't work with a maths with two signs, with two signs like that. You have to get one sign. That's the key. And when you look at it, when you have the plus and the minus, you have to get one sign. And the rule states that when you multiply a positive times a negative, you get a negative. So you end up with just one eventually. So if you start off with plus or minus, you end up with a minus. If you have, suppose you have something like that, that will be what?
A minus, sir. No, plus.
A plus, because when we're multiplying two negatives, we get a what? A positive.
Positive.
Right. All right. Any more questions?
So what we're doing now is different from that, the BAMAS method.
No, we're not. I'm not teaching bad math. Somebody just mentioned it.
Okay.
I'm not doing bad math. All right. Any more questions? All right. Okay, so we're going to look at, based on my calculations. Oh boy, I was trying to see if I can even do the fraction thing, but it's not working based on what I'm seeing here. All right, online teaching is pretty slow here because I would have covered so much in the face-to-face class. That's why I'm lobbying for an extra hour or two with you guys, All right, but let us do what we can do. Not sure. All right. Okay. No, we're going to look at what we call laws, a few laws in math. We're not going to look at all of them, but there's a few. All right. Actually, we're going to look at, for today, we're going to look at 3 laws. So just like how you have, you know, laws of a land, we have traffic laws, you know, there's so many laws, aren't there? We have so many laws, property law, you know, financial act law, and the parliament just passed a law the other day. I think they passed it. The sexual offenses are sexual harassment acts. Am I correct? Anybody knows about it? Hear about it?
Yeah, I'm aware.
Yeah, that's right. So every day people are looking at laws and, you know, to create. So, yeah. But in math we have laws. All right, and one of those laws are
basically things that govern how things work in the math world.
Right. And let me tell you, sometimes they see in mathematics, laws are not to be questioned. You just accept them. All right. Yeah, there's no proof for them. They're just natural. For example, 1 + 1 = 2. That's a law, you know. So there's no proof for that. We know that if you have 1 apple and you have a next apple, you get 2 apples. You know. So one of the laws we're gonna look at is what we call the commutative law. All right. So what this is really about, it's basically when we flip around an operation. That's basically what it's about. For example, 2 + 3 3 + 2. Wait, no, do we get the same answer? Yes, we do. So 2 + 3, 3 + 2, we get the same answer. No, so we therefore can say addition of integers, well, addition of let me use whole numbers. Obey the commutative law. Everybody following?
Yes.
Yeah, man. So when you flip around an addition, you get by the same answer. We could say since let me just drop this in. Since the left hand side is equal to the right hand side. All right. So addition obeys the commutative law. What about multiplication? Does multiplication obey the commutative law? Let's find out.
Well, when you flip it with the division.
No, we're talking about multiplication. Does it obey? What's 2 times 3? And what's 3 times? And what's 3 times 2?
6.
Okay.
You get the same. You get the same thing, Drew.
Yeah.
So therefore, since left hand side is equal to the right hand side, can say multiplication obeys the commutative law. Miss, you were saying something about division? Is it clear?
So I was saying, with the division, I would say it's not.
Give an example.
If you should flip it, let's say 2 into 6. Right. You're gonna get 3. Right? And if you should flip it 6 into 2, you're gonna get some decimal.
You're gonna get a third.
Am I?
Yeah, you're gonna get a third.
Okay.
Which is different from 3, right?
Yeah.
So therefore, we would say in this case that division does not obey the commutative law. All right? All right. Just mute your mic for me, please. You have a really noisy background. It's like your the fan is on you. So when it blows on you, we hear the breeze. All right. So that's a perfect example. Thank you so much. So as you were saying, let me just use your example. She was saying that 6 divided by 2 is not the same as 3 divided by 6. All right, because we get 2 in one instance. When we simplify it, we get 2. All right, and the other one is what? 1/3. All right, so we can say that the left hand side is not equal to the right hand side. Therefore, division does not obey the commutative law. All right. What about subtraction, class? What if I have 10 subtract 4 and I have 4 subtract 10? Do I get the same answer?
No, sir.
No, because I'll get 6 for the first one. Let me change this. So this is not equal. Not equal. And for the other one, we'll get -6. So we say since the left hand side is not equal to the right hand side, you can say subtraction does not obey the commutative law. Any questions? All right, now we have what we call the associative law. We have the associative law, all right? So it's something like this. If we have, say, example, 1 plus 2 plus 3, 1 plus 2 plus 3. All right, let's say we have 1 plus 2 plus 3, right? Now, what if I decide to add the first two and then add the third one? What would I get? That's 3 plus 3, right? Which is 6. But what if I decide on the right hand side to add the last two with the first? I'll get 1 plus 5, which is still what? Which is still 6. So 6 is equal to 6. So therefore, the left hand side is equal to the right hand side. So therefore, addition obeys the associative.
So, sir,
Yes?
is it the brackets that makes it different from the addition and or you would consider the addition as an associative law?
Both of them, you have to use both concepts, because what we use a bracket because the bracket is like an instruction. So the instruction is, think about it, you can't add 3 numbers one time. All right? You can't add 3 numbers one time. So you have to add 2 by 2s. So the bracket would indicate to us that we should work out the first 2. And then on the right hand side, the other bracket is saying that, hey, don't work out the first 2, work out the last 2 first. Get it? So it's like an instruction.
Okay.
So both of them work hand in hand. Because if I give you 10 numbers, you know, I mean, without any instruction, by natural instincts, you probably want to work out the first 2 to the left, not true?
Yes, sir.
But if I give you 10 numbers and I put a bracket and I put the bracket in the middle, I say, you know, something, add them first 2 numbers. Me say I must add them first 2 numbers. Those first 2 numbers first. That's what my rule is. So the bracket is like a, you know. Now, the same results for multiplication. Is it true? If I were to change these pluses to multiplication sign, would you get the same answer on the left and on the right?
Yeah.
You would, yes, that is true. All right, I'm tired of typing here, so I'm gonna do this. So if I have 1 times 2 times 3, and I have 1 times 2 times 3, and if I put these 2 brackets there, okay, don't work out those 2 for me, or work out the last 2, would you get the same answer? Answer is yes. 1 2s is 2, 2 3s is 6, 2 3s is 6, 1 6 is 6. So what's the implication? Multiplication obeys what? The associative law. So you can write down an example for me.
Yeah, Mr. Stevenson.
Yes, sir.
I think I missed some from the earlier part. I'm not sure if you could like scroll back a bit. Not sure if everybody got it.
All right. When I close this, it will go back to the original page. Yeah.
Okay.
Just get this off. All right. Can I take this off?
Yeah, sure.
Can someone second that?
Yes, sir.
All right.
Yes, sir.
All right. Okay. So right here, as I say, the same result for multiplication. So therefore, multiplication obeys the associative law. What about subtraction? Let's investigate subtraction. Suppose I have 10 subtract 4 subtract 2. I said work out those first two. Or work out, hold on here. Work out the last two. No, 4 from 10 is what? 6. 2 from 6 is 4. Can somebody tell me what this is? What this means? What is the answer for that?
-2, sir.
Check Mr. Brown. Check Mr. Brown.
Is it 10 minus 8?
No, you're close.
A -6.
Right. You almost yes, -6. You almost are brown how much money? $4. And you almost are brown again what? One next $2, aren't you? Say in total what? 6. I will know that 6 from 10 is 4. So we notice subtraction also obeys that what? That law, don't you? All right. So we can say subtraction obeys the commutative law. These are two.
Communicative. Associate.
Hold on. Hold on. Am I spelling this thing wrong the whole time? You know, sir. Oh yes, I'm sorry. It's not the.
We already discovered communicative.
Hold on. I'm sorry. It's the associative law, not true?
Yeah.
Oh boy.
Yes.
The associative law. Dot. All right. Any questions? All right. Can I take on this slide? Let me give you 30. Yes. Okay. Can somebody second that?
Yes, sir.
All right. Let me stay that down. So we're going to look at our last law for this segment. What is this? Okay. Now the other law that we're going to look at is called the distributive law. All right. Now the word distribute means to give out, not true. All right. Now, when you're in high school, do you remember your math teacher talking about removing the brackets? Have you ever heard that phrase before?
Yes, sir.
Yeah, man. Yeah, man. When you have brackets, what will you do them? Remove them, not true? No, the ability to remove brackets comes from a law called the distributive law. So sometimes you'll see the instructions, remove the following brackets using the distributive law. I said, what am I talking about? We only can remove the brackets. What am I talking about law? Right. So our ability to remove brackets is because of a specific law called the distributive law. All right. And it's pretty simple. There's nothing complex about it. So for example, if we have something like A bracket B plus C, what this is saying, you see, and I've mentioned this before, bracket means to multiply, not true? So
Yes,
this is actually A multiplied by B. Plus A again multiplied by C. And you could go further that you're going to get AB plus AC. So that's what the distributive law is about. All right. Let me show you something, because some person might think, let me show you something. Suppose I have B, you see? Subtract C. All right, I'm gonna say something to you, and I hope you remember this. You see this plus sign here? That plus sign, let me pick it up a little bit. All right, probably it's too big. You see that plus sign? It is always there. All right, it's always up, and it is not because this is plus. Why is this plus enough? I'm gonna show you why.
It's positive.
Well, it's because I always put a plus there. Because in this case, look at the second example. That's A bracket B subtract C. All right, so let me show you what's going to happen now. So this is going to be A multiplied by B. And what did I say? Oh, I was put a plus there, don't you? Agree? Plus what class? A again, no. Multiply by what?
C.
I can't see. Only.
B.
Negative.
It's negative C. So I'm saying? So it's A times B and A times negative C. And then no, you'll get A times B, which is AB. Then you have the plus. And then no, right? So right here, so remember the rules I've been telling you about? A positive times a negative gives you a what class? What's a positive? A negative. And what's A times C? AC. And then no, we can merge these two together, and that will give us another negative. All right. Don't worry yourself about this here. I'm actually jumping ahead. All right. But the main point I want for you to remember is that you always put a plus there. So, all right. Always put a plus right there. So. Let me just ask you to do this. This is a little activity. I want to just, how do you work this out? Oh, sorry. You know, let me not. I think I'm diverging a little bit. Let me just use this. Let me use this. 3, 4 plus 7. All right, look at that, class. Example 3. Now, I can use the distributive law here, not true? I will get 3 times 4 plus 3 times what?
7.
Times 7. All right. I'm going to know that that's 3 4s 12. 3 7s 21. What's 12 plus 21?
33.
33. But you could always add these two numbers, don't you? Because 4 plus 7 is what? 11. 3 11s 33. All right. But I'm not showing you how to use the distributive law. Any questions?
Think I'm following.
No, man.
Sir.
Yeah.
So because using the distributive law, the 3 outside of the bracket has to be applied to both numbers within the bracket.
Right. It's like we're distributing. I suppose I have 4 plus 7 plus 6 plus 8. It's gonna go like this. Bum, 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 bum. It's like we're distributing it. You get it?
Yes, sir.
Right. So this is forever. It doesn't stop. Let me get a little joke. You know, I once, I can't remember, honestly, it's been a long time, but I remember, like, I think I got hired at a school, right? And I was teaching an upper school class, and you know, I think this was, I'm not hypothesizing the question. Suppose it was like 2, right? 2, 4, and 3. Right, you know, and that them say yes, one sir, me know who that, me know who use this group. This is what they do. Them say, all right, sir, this is what you do. You say 2 times the 4 plus 3. That's what they say, no? So they say, yes, man, sir, I say it, man. So big up yourself, sir. Big up yourself. So I say, so what about, shouldn't you put a 2 right here, so? Like, should it be 2 multiplied by 3? And the person said, the student said, no, sir, and so would be, man, and so, sir. I'm asking you, so why? Why is only you use it 1 time? So, sir, because when you use it with the 2 times 4, it's done. You can't use again. So like it finished, like it done off. So I said, so no, brother, and I said, go on. It goes on and on and on. You know? So in fact, it should be 2 times 3. All right. All right. Can I? Yes. Want to say something?
So the number that is outside the bracket is supposed to be used to times whatever is inside the bracket.
Boy, a beer breeze my ear now.
I'm sorry. So what I'm saying is basically to sum up, the number that is outside the bracket is used to times whatever is inside the bracket.
Yes.
Basically.
Yeah. And you use that number, you attach it to everything that's inside it, not only once.
Yeah. Okay.
All right. Can I take this down?
Sir,
Yes, sir.
is there a law that says just like how in distribution, anything outside the bracket basically multiplies what's inside the bracket? Is there one that says what's outside the bracket only multiplies what only the first, as you were showing not too long ago?
No, that was a incorrect statement. The students were doing something
No,
wrong.
yeah, I get that. But what I'm saying is that if it's a case that there is one that does apply to that one, a lot that apply to that one.
As to just one number alone?
Yeah, as to only one number.
Why you ask that?
No, can we make recall doing something like that in the past, but I don't remember if it wouldn't go to distribution law, but I don't remember what it was.
You were taught wrong. You were taught incorrect. So there's no law like that.
Okay.
Yeah, there's no law like that. All right. Any more questions? Everybody okay?
Well, for me, I just miss some of the
Yes, sir.
notes that you were jotting down. I don't know if I could like get those if you could like scroll back on some of the notes you're writing off, because I was, my fault I didn't write it down. I'm not sure if everybody got it.
Oh, you mean the yeah, man, I'm gonna close this. Everybody have this?
Yes, sir.
All right. I'm just gonna do a quick check-in to see if everybody's awake and are alive. Tamar, are you alive?
Yes, sir.
Sarita, are you there?
You just said Frita, sir?
Yes.
Yeah, I'm here.
Okay. I'm just zooming in on persons. Novia, are you there? Novia gonna sleep. Shellyan, are you sleeping?
No, sir.
Not asleep.
No, sir.
Ronaldinho, are you playing football? Or are you paying attention?
Yes, sir.
Or both?
Yes, sir. I'm there.
Romario, are you there, sir? And Richard and O'Shane?
Live and in living color, sir.
Yeah, right, that's all.
Okay, good. I'm just zooming in. Don't feel if I don't call you. I'm just randomly just scrolling through. Goodwill, are you there? Or are you gonna sleep?
Here, sir.
All right. Emily and Kendra Lee, are you there?
Yes, sir. I'm here.
My name twice.
Marlene, I'm sorry, I'm just randomly. Marlene, are you there? I'm sorry.
Okay.
Yes, sir. I'm here.
All right, so I shouldn't call your name twice, ma'am. Sorry. Camille, are you there? Mrs. Camille, are you there?
Yes, sir. Yes, sir. Yes, sir.
Am I correct? Is it Mrs.?
Yes, sir.
Not Miss.
Mrs.
Okay, you gained an S.
Yes, sir.
So what the man gain? Or him lose?
I don't know.
All right, Miss Marshall, are you there?
Your wife.
Yes, I am.
All right. Okay, and Anna K, are you there?
Yes, I'm here, sir.
All right. What about Luciano? Here I come, Ja.
I'm here.
You know that song?
No.
Yeah, sir. That's probably Lucia. You know, this the artist Luciana, right?
I do, but I was not actually named after.
Oh, is it opera singer? Pavarotti? All right. Maybe somebody that All right. But all right, you can't stop laughing for 5 minutes. All right. Okay. O's iPhone. Who's O's iPhone?
It's me. My name is Owana.
So okay. You're okay. Yeah. I would love for you when you enter the class, you have your full name. All right. Chantalee Plummer, are you there?
Yeah.
Chantalee? Chantalee gonna watch news.
I'm still here, sir.
Still here. You sound like you're flying. You sound like you're in a helicopter. Are you fun
No.
so?
No, I'm
I
fine.
fun go so. You know, say fun can sound like helicopter so many times. You know that?
Yeah.
Yes. Yes. All right. Boy. I think I get myself in trouble because I don't know if I call everybody name. I'm messing up. Also not call for me name. Oh, have mercy. Goodwill, are you there? I think I called your name already, don't you? Is it Davia Dolo? Are you there?
Yes, I am.
All right, cool. All right, so we're gonna look at
Sir, I'm gonna hear my name.
same thing. Oh my.
And I am here as well.
Some peace. But no, Miss Clark, Miss Clark, I didn't call you because you've been speaking the whole time. So you know, all right, who never hear the name must big up on themselves and company man.
I hear my name.
All right, okay. Tell you what, just state your name. Just state your name. I am such and such. I'm sorry.
Carly Hamilton.
All right.
Jenny Forrester.
Valicia Jarrett.
What everybody want to call in.
Susan?
Yes.
Yes, Adrian.
Jess.
I was wondering if you could like scroll up a bit so I could jot something down real quick, like the stuff you were writing earlier.
The stuff I was writing. All right.
Yeah, because I missed out some from.
All right. Is that okay? You want me to go further?
A bit further, if you could.
Yes, sir. Go a bit further.
Right there?
There are other people here that missed out a bit. Like.
Oh man, not talk about other people, man. Talk about you, man. Cause yeah. Talk about you here. It's like as a boy, everybody didn't write it out.
Sir, I'm right at OB.
You're right at OB? Right here, sir?
Yes. Yes, sir.
All right, cool. All right. So I must apologize if I didn't call out the name. I was just fooling around just to check to see if you guys are awake and attentive. All right. So let me give let's take a little 3-minute break here while the person writes this off. So 3-minute bathroom break, water break, or TikTok break. I don't know what you guys do when you're going to break.
Sir? Sir?
He said break. I think he might have to take him on himself.
Okay.
All right. Are you guys through with the writing of the notes? Can I scroll down?
Yes, sir.
All right. All right. So we were looking at the distributive law and some other stuff. All right, so I think I'm gonna stop here because you know it's 8:39 and